we're gonna go tackle this grand engineering challenge to build something nobody's built, to do something nobody's done yet. And I was like, I'm quitting my job, I'm taking a pay hit, let's try it, let's do it.
The most dangerous part of building fusion is not all the radiation, the voltage. It is the whisper that says, you're wasting everyone's time. In a plain warehouse, a startup called Avalanche chases the reaction that smaller than a Toyota Tundra powers the sun, but they want no giant tokamak, no billion-dollar facility, just high voltage, fast rebuilds, magnets, and a team willing to fail in public. They hit early wins, slammed, then found a clue in old Soviet into a brutal instability experiments. Watch how doubt becomes a pivot, and how one bright flash rewrites the plan. The doubt. Some days, the team asked the question frauds out loud. Fusion is brutal because you are trying to make a thing work that has never worked in your hands before. When the graphs do not move, fear fills the gaps. A founder can raise money, hire talent, and still stare at a machine that refuses to behave. Avalanche lived inside that pressure. They were not going to finish what they said they would finish. They promised milestones, and then reality hit. Worse, they did not even feel like they had a proper fusion machine yet. Stress turned into anxiety. The plan on the slide deck did not match the metal on the floor. It felt fragile because even the best day, bad shot could erase a month of confidence and momentum quickly. That is the daily grind. In fusion, that inner voice is loud. You are not good enough. You are wasting everyone's time, and your team is losing faith. But the story starts there, because doubt forces a decision. Either you quit, or you learn faster than the fear can grow. Their bet was simple. Build small, test often, and treat every failure as a data point, not a verdict. Why fusion? Why small? The founders did not come from nowhere. While they were among the first 10 people working on the New Glenn reusable rocket, that job carried a dream. Millions of people living and working in space. One started at Blue Origin in 2014 and met Bryant. It also carried a hard lesson. Chemical rockets alone make that dream painfully slow and costly. Nuclear looks like the answer, but launching a fission reactor brings safety worries and heavy systems. So their eyes went Tinto fusion. If you want a real space economy, you need energy that is dense, clean, and scalable. Fusion is what powers the sun and, by extension, almost everything alive on Earth. In simple terms, you take light atoms and force them together so they become heavier atoms, releasing huge amounts of energy. Around 2018, one of them told Bryant, "I want to do a fusion startup." Bryant wanted in. At home, the message was practical. Get good insurance, and please bring home a company hoodie. It meant quitting a stable job and taking a pay cut. They looked around and saw that most fusion machines are enormous, and that size makes learning slow. Avalanche wanted rapid learning, Toyota Tundra, so they wanted a reactor smaller than not like a national lab. They could iterate like a startup. The Orbitron idea. Fusion has many confinement schemes, meaning different ways to hold and heat plasma long enough for it to fuse. Accelerators are another big magnetic approach. There is also laser fusion. Tokamaks are the mainstream path. Then there are magnetic mirrors. And in a more niche corner, there is electrostatic fusion, where high voltage shapes the motion of ions. Avalanche treated this like early aviation. At the start of flight, people tried many wing shapes. Some looked silly, some failed fast, but a few patterns emerged, and those patterns became airplanes. Their pattern was a hybrid. Use electric fields to confine and heat ions by pulling them into a potential well. Use magnets to confine electrons, like a magnetron in a microwave. Electrostatic heating can be wildly efficient on paper because voltage can apply a strong force over short distances. The catch is that pure electrostatic devices often struggle with losses and stability. So Avalanche asked a sharp question. Can we operate between purely electrostatic and purely magnetic, taking the best parts of both and cutting down the worst parts? They called their approach the Orbitron hill on fusion, basically running a One founder went red-directed PhD. He read books, papers, and old reports until the concept felt real. The mission became simple to say and hard to do. Prove an electrostatic path can climb toward net energy. A warehouse, fast builds, real neutrons. The seed goal was they moved into a warehouse with about 13 people. They avoided multi-million-dollar clean rooms. They used clear. Build an Orbitron, mostly electrostatic for ions and magnetic for electrons, and make neutrons with deuterium. Commercial parts. Speed was the advantage. In a giant reactor, one bad design can waste years. Here, a new design could happen in 2 or 3 weeks. They built the first machine, bolted it together in February, pushed it up to roughly 50 to 80 kilovolts, and saw fusion neutrons almost right away when they ran deuterium. That early proof mattered. It showed they could go from nothing to a working first Orbitron with $5 million or less. That success helped unlock Series A funding. But Series A was not about a janky demo. It was about doing things no one had done in electrostatic fusion. Increase the voltage per electric stress, volume, what they call so the field traps particles deeper and drives more collisions. Hit 300 kilovolts. Shoot more than a milliamp of ions into the machine. Integrate superconducting magnets. Then push plasma density to 10 to the 11 per cubic centimeter. They iterated through about 20 designs on the way to 300. The plan was like a rocket program. Prove each subsystem, then stack them together. 100 kilovolts, building and breaking hardware until the lessons stuck. Getting Series A felt like 2 emotions at once. Yes, we did it, and oh no, now we have to deliver. Bigger team and more money. With a B, the experiments had to stop being lucky and start being repeatable. The density problem and the Soviet clue. Then came the wall. In 2024, they were supposed to hit their density milestone. They had voltage, the last technical milestone for Series A. They had beam injection. Density refused to rise. Density sounds simple. In a fixed volume, pack in more ions that can fuse. But it is a 3-part demand. The ions must be dense, they must be hot, and the condition must last long enough to matter. If you only achieve it for a blink, it is not a power plant. When they pushed for higher density, a rotating mode, an instability appeared. They compared it to a washing machine. Clothes clump on one side, rotate, and the whole machine shakes. In their plasma, that clump meant particles slammed into the wall. The plasma leaked out instead of building up. By April 202-5, the mood turned dark. Could not stabilize it the way they planned. They admitted there was no clear path to net energy in sight. Still, they acted like scientists, not victims. 100 kilovolts to learn how they pulsed the cathode from 0 to 1 how the mode starts. The traces looked odd, and adding shear that could calm the instability. Their plasma physicist, Eric, suggested the pulses might be spinning up the plasma. One founder remembered a concept from his turbulence PhD. Under the right rotational shear, messy turbulence can be ripped apart, and a smooth flow can form. At the same time, a teammate named Jesus pointed them to Russian experiments from the 1980s and 1990s, including one called PSP-2. Those experiments used strong current pulses to spin plasma quickly, and the shear broke up the turbulent mode. Suddenly, Avalanche had both a theory and an old proof that it could work. Gin, first light, and the number. Friday became rebuild day. The weekend was once they believed the idea, they moved fast for baking and setting up. Monday was for tests. They added new electrodes, new probes, and different end caps. They fought vibration that was throwing results off, and they named the upgraded machine Gin and parts to keep the structure steady. After Gin Erso from Rogue One plans. They were borrowing Soviet-era tricks to save their own deadline. The big day was first light, the defining experiment, their Series A final exam. They expected a bright flash as the gas ionized. For a moment, a small volume of gas would be driven toward a fraction of the speed of light. Right before the shot, someone quoted Edison. Another asked what separates a great scientist from a heretic. Every failure still teaches you something. The answer was proof. Then the flash came, the room erupted, and the real win arrived later inside the data. After weeks of analysis, they measured about 4 × 10 to the 12 per cubic centimeter. They had beaten their Series A density goal by roughly 40 times. A month later, they were running hard. It did not mean net energy yet, but it changed the risk. Doing dozens of shots in a day, even 50+ tests in one Friday. The instability that made it feel like a doomed science project now looked like an engineering problem with knobs and schedules, aiming higher. So they kept iterating. More confinement time, more voltage, more energy. Fusion does not reward confidence, it rewards persistence and a real climb up the triple product chart. Avalanche still has mountains ahead. More stable operation, longer confinement, higher voltage, and the hard climb up the Fusion triple product chart. But their story proves something. A small team, rare in energy research, using commercial parts and relentless iteration, direction before time runs out, can learn fast enough to change. They faced the washing machine rotating mode, admitted they were stuck. From that, they reached densities once called impossible, and then used rotational shear to break it apart. Now the real engineering sprint begins, and that could reshape life on Earth.